Ever stop and wonder what connects the flame on your stove, the fuel in your car, and even the plastic phone case in your hand? I mean, they seem totally different, right? Well, the answer is this incredible family of molecules that are, and I mean this quite literally, the engine of our modern world. Just think about it for a second. That gas in your stove, the fuel powering your car. And yeah, even the plastic you're probably holding right now, they all share a common chemical ancestor. So what is this invisible thread that ties all of these things together? Well, it all comes down to one really simple, elegant type of molecule. The hydrocarbon. And the name pretty much says it all. These are compounds made of just two things, hydrogen and carbon atoms. That's it. But don't let that simplicity fool you, because from those two elements, an absolutely mind-blowing amount of complexity emerges. To really get a grip on them, we've got to look at their family tree. And the secret to this entire family, the thing that defines everything, is how those carbon atoms hold hands. It's all about the bonds. So we can basically split them into three main branches. First up, you've got your saturated hydrocarbons. They only have single bonds between their carbons. Then you've got the unsaturated ones, which have these more, let's say, exciting double or triple bonds. And finally, there's a really special group called aromatics, which have this unique ring structure. All right, let's start with the foundation, the most basic branch of the family, the alkanes. The best way to think about their single bonds, it's like a firm, stable handshake in the world of chemistry. And because of that firm handshake, alkanes are super stable. They're not very reactive. They kind of just like to keep to themselves. In fact, their old nickname was paraffins, which comes from the Latin for little affinity. Basically, they're not too interested in mingling at the chemical party. But that stability makes them absolutely perfect for one key job, being incredible clean burning fuels. You know the LPG you use for barbecue or the natural gas that heats your home? Yep, those are alkanes doing their thing. But okay, here's where it gets really, really cool. What happens when you have the exact same atoms, but you just, rearrange the furniture a bit? This brings us to the idea of isomers. So take a look here. We've got pentane, which is just a straight chain, and then we have 2,2-dimethylpropane, which is scrunched up into a compact little ball. Now get this. They have the exact same atoms, C5H12, but just look at that difference in boiling points. Wow. Just by changing the shape, the temperature needed to make it boil plummets. Why? Well, the long chains have way more surface area, so they can stick to each other better. You need more heat to pull them apart. It just goes to show you, in chemistry, shape is everything. Okay, let's move on to the next branch of the family, the alkenes and the alkynes. Now, if alkanes have that firm, stable handshake, these guys have bonds that are just ready for action. These are the creators. And this really gets to the heart of the difference between these families. Those stable single bonds in alkanes, perfect for fuels. But the reactive double and triple bonds in alkenes and alkynes, well, they make them fantastic chemical building blocks. They're practically designed to react and become something totally new. So how's that work? It happens through something called an addition reaction. See, an alkene molecule has that double bond which is packed with reactive energy. When other atoms get close, the weaker part of that bond basically just opens up its arms to welcome them in, and boom, you form a brand new, more stable molecule. This ability to just keep adding new stuff is basically a chemical superpower. It's what allows us to take these tiny little units, called monomers, and link them together into these giant, long chains we call polymers. And that, right there, is how we get things like polythene, the plastic used for everything from shopping bags to water bottles. And that brings us to our final, and maybe most famous, hydrocarbon, benzene. This molecule is an absolute superstar, a ring with a legendary origin story that actually started with a chemist's dream. So meet August Kekule. Back in 1865, he was completely stumped by the structure of benzene, C6H6. The numbers just didn't add up for a straight chain. And the answer, as he famously told it later, came to him while he was dozing off by the fire. He dreamt of atoms dancing around, forming long chains, kind of like snakes. And then he saw it. In his own words, one of the snakes had seized hold of its own tail, and the form whirled mockingly before my eyes. A snake biting its own tail. Eureka! It had to be a ring. So the dream gave him the idea of a ring, but the reality is actually even cooler. Benzene is what we call a resonance hybrid. Instead of having fixed single and double bonds, 6 of its electrons are delocalized, meaning they're shared equally across the entire ring, just whizzing around in a continuous loop. And this sharing gives the molecule incredible stability. And because of that special stability, the benzene ring is one of the most important building blocks in all of chemistry. It's the backbone for countless dyes, drugs, and all sorts of other advanced materials. So let's tie this all together, shall we? From these simple carbon-hydrogen bonds, we get a whole world of unbelievable chemical diversity. Here's the big takeaway. You've got the alkanes with their stable single bonds, which make them amazing fuels. You've got the alkenes with their reactive double bonds, making them perfect for building plastics. The alkynes have super reactive triple bonds used in things like acetylene for welding. And finally, the aromatics, that uniquely stable ring, give us the foundation for dyes and medicines. From the fuel in our tanks to the plastics in our homes and the medicines that keep us healthy, these simple little molecules of carbon and hydrogen have, no exaggeration, built our modern world. And that leaves us with a really fascinating question to chew on. What should we build with